Good. So our last section we're going to look at in chapter 9 is the first part of 9.2, which is on what we call polar graphs. So everything that we did yesterday and everything we've done prior to yesterday from the beginning of the year has all used a rectangular coordinate system. Okay. In a rectangular coordinate system, your graph paper looks like this. It's a grid-based system where you have left and right movement and you have up and down movement, okay, to get to a point. Now, usually we have our axes drawn in like that. The horizontal is called the x and the vertical is the y. Well, there's other ways we can graph besides on a square grid, and that's using a polar grid. You don't like polar? Why?
That's scary.
I've seen that before, and I didn't know that it was like.
What don't you like about polar? Wait, have you done anything in polar before? No? Oh, well, wait till you see it. It's not that hard. Polar is really good if you want to draw shapes that are circular. Polar is not as easy for drawing things that are straight lines. So we already have a good system for drawing lines. We just use like a y equals mx plus b, and we use that kind of grid. Right? But circular shapes are a real pain in this system. Okay? Much, much easier to do in that system. So when you do polar, to really understand everything in polar, probably take about a week of like 4 lessons. We could go over most things in polar, but we're going to spend 1 day on it. So what I want to do is show you the same shape drawn in 3 different systems. The function system, parametric, and polar. And I want you to look at it and tell me which equation, when I'm done, looks the simplest. Right. So I'm going to start with a function. Okay. That's the mode we've been using all year. I want to draw, and I'm going to do a circle. That's the shape I'm going to show you how to draw. So if I want to draw a circle as a function, that is the formula. And it's not even really a function because the circle fails what test?
Vertical line.
Fails the vertical line test. So I can't even really draw a circle this way. But the only way I can do it is to kind of draw the top half and then draw the bottom half as 2 separate things and just have them look like they're together. It's the best we can do. So let me draw a circle with a radius of 3. So what I'm going to do is, anytime I want to type something in on the graphing calculator, I need to have y by itself. Okay? So I have to take the equation that they normally use for a circle, and I have to get this alone so I can type it in. And if you subtract the x squared to the other side, and then take the square root, you can get the y by itself. All right, so I'm going to type that in, and again, I'm going to do a circle of a radius of 3. So 3 squared gives me how much? 9. So I'm going to put a 9 right there when I type it in. I don't have to do a radius of 3. I could do any radius I want, but let's just do 3. All right, so we're going to do the square root of 9 minus x squared. So second square root, 9 minus x squared. And when you take a square root, you need the positive and the negative. This is what's going to give me the top half and then the bottom half separate. Square root of 9 minus x squared. All right, I'm going to do zoom 6, and then I'll fix it with zoom 5 to make it look not distorted. So zoom 5. And that's the best that I can do to draw a circle as a function. It's really not even a circle. It's just 2 semicircles kind of stuck together. They don't even connect in the middle. And remember, because when you start drawing lines that get close to vertical, the calculator has trouble with it. And that's what's happening on the edge of this circle. It's getting pretty steep. Okay, so there's your picture. And here was the formulas that we used. Any question on that first one?
That was on a normal graph. Right?
Yep, that was the normal kind of graphing that we're used to. That was as a function. All
So
right.
you kind of have to get it into like a sort of slope-intercept form to add to the graphic.
Well, yeah, you got to get y by itself. So there's a little bit of work to do that, and then you got to type in two different things, and then you got to, yeah. So it's a little bit of work to graph a circle, and that's again as good as I can do. All right, now let's go to parametric. When we do parametric, how many equations do you have to type in to get a single picture? 2. The first equation is for the x's, and the second equation is y. And we learned the equation of a circle yesterday, and actually we did the exact one in the homework. What would be the x formula for the equation of a circle with a radius of 3? Yep.
Is it 3 cosine t?
3 cosine t. Yep, good. And we changed the variable because you use x when you're doing functions. You use t when you're doing parametric. And what about the y formula? 3 sine t. Okay, so a little bit nicer formula. It does have trig in it, but at least it doesn't have me having to get like square roots and things like that. Okay, so let's type that in. Let's go to mode. Let's go to parametric. And we're going to type in 3 cosine t, 3 sine t. Okay, and hit graph. And there you go. I didn't set my parameter from 0 to 360. Sorry. So let's go t min is 0, t max 2 pi because I'm in radians. Now I'll get a full picture. Okay, so there's your picture. And that actually connects. That is a circle. Who cares it fails the vertical line test? We're not drawing functions. We're drawing things parametrically. So we get a nice picture. And here was the formulas that we used. Put those right there. Okay, so that's parametric. Any questions on that one? All right, now I'm going to do a third way, and this way we haven't learned about yet, and that is polar. If I want to draw a circle in polar, well, now I'm going to change my mode to polar. So go to polar. And now it says r equals. Well, I want to draw a circle that has a radius of what?
1.
I'd like it to match the other two.
3.
3.
Oh.
Put in a 3. That's it. Okay, so it's just r equals 3. And there's your sketch. So that's, well, I'll let you decide which equation you think is the simplest. Picture looks pretty much the same as the last one. You wouldn't know that I did that in polar unless I showed you the mode on the calculator because it doesn't say anything here about being in polar. But if I show you the y equals screen, now you know it was in polar because it has an r. That is the letter you're going to see us use today when we do things in polar.
See, that's less scary. That circle graph, that was scary.
So there's all 3 systems for drawing a circle. Which system has the simplest equation?
Polar.
Polar. Yep. So drawing in polar, very, very easy for circles. Again, drawing lines can be done, not as easy. Lines are much better in y equals mx plus b, which is what we're used to. Okay. Any questions on that? So that's the advantage of polar. Makes certain shapes extremely simple to draw. At least the formula is extremely simple. So we're not really even going to get into drawing a full shape in polar. I'm going to show you just how to graph a single point in polar. Just one dot. So this is what polar graph paper looks like. Instead of being a grid that's rectangular, it has circles. It also only has one axis. There's not 2 axes here. This is your axis, that part right there. And that is called the polar axis, just that section. Everything is going to be measured generally from that line right there. This point in the middle, what do you think we call that? You can call it the origin, or in polar, you can also just call it the pole. Now, when we do a coordinate on an XY graph, how many numbers are part of the coordinate?
2.
2. We have 2 numbers, a number for X, a number for Y. When we start writing coordinates in polar, they are also going to have 2 numbers. But we're not going to call the 2 numbers X and Y. Oh, same thing. We're going to call the 2 numbers R and theta. So R is going to measure a distance. Theta is going to measure rotation. That's how you graph points in polar. It's based on a rotation amount. But R is a distance. So what I'm going to do now is go through the different cases that you can have, like what happens if R is a positive number, what happens if it's a negative number, and then what happens if theta is a positive and if theta is a negative. Okay, so that's how you write a point in polar. I probably have an example. This one. 3, 45 degrees. That is a polar point. -2, 75. 3, -60. Those are all polar points. So when you're graphing it, you start with the first number, which is R. And I'm going to tell you how you do that. Yep.
Can the angle be in degrees and radians?
Yes.
Okay.
Yep. Angle can be in degrees or it can be in radians, like that. Yep. If it's hard to work with it in radians, you could manually change to degrees. It's an extra step, but you could. All right. So to graph the point, the first thing you do is look at R. R is pretty much follows the same rules as you treat it like an X. If R is positive, you're going to start from the origin and you're going to move to the right the number of units indicated by R. If R is negative, you're going to start at the origin, you're going to move to the left. Now, just like with regular coordinates, you can have decimals. So you could move 3.5 units to the right or 1.5 units to the left. You can do that. Right, so you start by going left or right, the number of units indicated by R, and then we have to take into account theta. Now, theta is a rotation. What are the 2 directions you can rotate in on a circle? Yeah.
Clockwise and counterclockwise?
Clockwise and counterclockwise, and that's going to be controlled by if theta is positive or negative. Which way do you think you would rotate for a positive angle? Counterclockwise, the same way we've done it all year. If your angle is positive, you're going to rotate counterclockwise. If your angle is negative, you're going to rotate clockwise. And that's pretty much the 2 steps to graphing a point in polar. You move left or right, and then you do an amount of rotation. Okay, so the next 5 or 6 problems, we're just going to practice graphing points in polar. And the way it'll work on the test, there'll be a grid. You'll be able to click on that grid, put a dot anywhere you want, and then you can drag the dot and move it if you put it in the wrong spot. And that's how you'll graph points on the test in polar. Yes?
Is there a reason that we go counterclockwise instead of clockwise?
That's just always the convention when you label your angles, like 0, 90, 180, 270. It just always goes in a counterclockwise direction when it's positive. I don't know why
Just because.
they use that convention. Yeah. I mean, it makes things work when we start doing trig. Because the sine of 90 is the y value, and sine is supposed to be 1. Whereas if you went backwards and you called this 90, then it would come out to -1, so it would be backwards. Right, so let's graph the point 345 degrees. You could really graph every problem I'm about to do on the same grid, just number which example is which. But I have a new grid for every problem. All right. What's the radius in example 1? Yep. 3. And because it's a positive 3, we're going to start by going 3 units to the right. So you're going to start right there. That's just a temporary x. I'm going to get rid of that in a minute. But that's where we're going to start from. And now from there, we're going to rotate. How many degrees are we going to rotate? 45. And which direction are we going to rotate? Counterclockwise. Okay, so when we say direction of rotation, don't say up, down, left, or right. Say clockwise or counterclockwise. So counterclockwise puts you about right there. 45 degrees is halfway towards the vertical. And that's how you graph the point, 345 degrees. And then once you start graphing, hundreds and thousands of points, that's when you get a whole picture like a circle or any of the other shapes I showed you yesterday. But we're just going to do single points. Let's try this one. -2, 75 degrees. What's going to be my distance from the origin this time? Yep.
-2. Or it's just 2.
It's 2. Yeah, the distance is 2. And then it's going to be 2 units to the left because it's negative. So you're going to start here, and now that is the starting point for the rotation. Okay. So now from here, you're going to rotate how many degrees? 75. Which way? Counterclockwise. So 75 degrees. Well, if I went all the way to this line right here, that would put me at what?
90.
That's 90. So we want to be a little bit before.
So it doesn't have to be like accurate. It just has to be like an educated guess.
Yeah, it has to be reasonably close because the ones on the test are going to have these grid lines.
Okay.
So you'll be able to tell. Like if I was doing it on this one, this is 180. The red one in the middle is 225. And then down here is 270. Let me zoom out, I can't see the whole thing. All right. And then in between, you've got your other angles. They go by 15s. So this is, let's see, 0. I think this one would be 15, 30, 45, 60, 75, 90. So since they go by 15s, we could get a pretty accurate picture. 75 would be on this one. If you started here and then you rotated, that amount that I just did, that's exactly 75. Yeah, so the grid will help you. Hey, any questions on that one? So that's a negative radius, positive angle. Let's try positive radius, negative angle. Okay, what's going to be my distance to the origin this time? Yep. 3. And we're going to start by going 3 units to the right. Yep. Thank you. You'll be right back. So 3 units to the right. And now, how many degrees are we going to rotate?
60.
60. Which way?
Clockwise.
Clockwise. So that's 60 degrees. That's 2/3 of a quadrant, because a whole quadrant is 90. So 60 degrees, go halfway, and then go a little bit more. Again, with the grid lines, it'll make it a little easier, but that's about where you want to end up. 3, -60. Any question on that one? All right. Let's try one this time. That's a negative radius and a negative angle, this time in radians. All right. Distance to the origin would be how much? Yep.
4
4. And we're going to go to the,
left.
okay, so let's start there. 4 left. And then we're going to rotate how many radians?
1.5.
Yeah, 1.5 radians, or 3 pi over 2. And which way are we going to rotate? Clockwise. How much? Where does 3 pi over 2? If I rotate clockwise, where does that put me? Yep.
Is that a good 270 mark?
Yeah, the 270 mark. So down at the bottom, right? 3 pi over 2 is 270 degrees. That's 3/4 of the way around the circle. So if I draw this, you went left 4, and then you went like that. That's how you got there. Okay. So let's change it to degrees, just because I want to try something. What would be another way to get to that point, besides the way that I have up there now? Yep.
You could add 360 to 270.
Okay.
make it
So what would
positive.
that give me for a coordinate?
Negative 490.
-4.
Oh, wait, did I do that wrong?
No, you can do -4, but you're gonna have to change what you said a little bit.
90 degrees.
90 degrees, yeah.
Oops.
So -4. 1, 2, 3, 4. 90 degrees. Counterclockwise. Yep. How about another way? Yep.
Could use positive 4 maybe.
+4, -90. 1, 2, 3, 4. -90 brings you that way. Yep. And one more way. Yep.
Both positive.
Okay. And what would they be?
Positive 4, positive 270.
+4. 1, 2, 3, 4. +270. Just like that. So, how many different ways were there to get to that point? 4. Okay, so in polar, there are up to 4 different ways to get to the same point. How about if I had a point right here? What would be one way you could get to that point?
4360.
Which would be the same as
40.
40. If we count adding 360 as a different way, then yeah, there's an infinite amount of ways. Because you could just say go to the right and then go around 13 times and then stop. But I'm only going to count negative, 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 positive, positive, negative, positive, positive. I'll count those as the 4 ways. So yes, 40. What would be another way? Yep.
Negative 4 180.
-4, 180. So that would bring you left 4, and then you'd be rotating 180 degrees around, going on the bottom half. And one other way. Yep. -4, -180, left 4, top half. That's it. There's only 3 ways to get to that point because it's on the axis. So when you have a point that is on the polar axis, there is only 3 ways to get to it. When you have a point that is not on the polar axis, there's 4 ways. Now compare that to having something like this. Let's just take this one. What's the coordinate for that? 3, 1. What would be another coordinate for that? Yeah.
If you flip the graph, it could be negative 3, 1.
Okay.
Well,
Or
negative 3,
1,
1.
negative 1,
puts you-
3, negative 1, 3. Oops.
Well, negative 1, 3, that puts you up
If you,
there.
if you flip the graph, if you like moved it,
Well, we got to land in the same
it'd be a
spot.
transformation.
Yeah, no transformation. I want to be in the same spot. How else can you get to the point 3, 1?
No other way.
There is no other way. When you're dealing with rectangular, there's only one way to get to any point that I put on that graph. In polar, up to 4. Okay, so that's a big difference between rectangular and polar. Now, which answer is correct? All of them. Just usually in the directions, they'll tell you, write your answer with a positive radius and a positive angle. Okay? Or write your answer with a positive radius and a negative angle. And the easiest way to figure out how to change from one to the other, you could just make a sketch and just look at your sketch, and that'll help you visualize it. You could think of things like, all right, if I make the radius negative, then I could subtract 180, or if I make it positive, then I could subtract 360 from 270 to get negative 90. So you could try to figure out all kinds of formulas involving 180 and 360. I think the picture's easier. So, all right, let's try 0 pi. Okay. What's going to happen with this one? What's going to be my distance from the origin? Yep.
Wouldn't it just be plotted on the pole?
Yeah, it's going to be right at the pole, right there. But then you've got to rotate pi units. So that's 180, like that. And that's your answer. Yes.
Go to the bathroom. Yes, sir.
Yeah. All right. So any question on that one? So the rotation doesn't matter. Right? No matter how much you rotate, if it's at 0, it stays at the pole. So 0 comma anything, it's always at the pole. How about we'll switch it and make it something comma 0. Is that going to be at the pole? No. Where's that going to be?
Just 2.5 to the right.
On the polar axis.
That's on the polar axis.
Oh, I remember the word.
Yep. And it's in between, that's fine, just like grid. When we have the grids, we can go in between the grid lines. It's 2.5 units to the right. Okay, so that's every different case you could have. Positives, negatives, and zeros. So any question on any of these polar graphs that we just did? So now, again, writing down what we already realized, there's more than one way to get to a point in polar, up to how many? 4, but if you're on the polar axis, you only get 3. Yep. All right, so the last 2 things we're going to look at is changing from polar to rectangular and rectangular to polar. All right, let's start with polar to rectangular. When I have you change from polar to rectangular, what do we call the 2 things that I give you in polar? The radius and the angle, theta. And if we're going to change to rectangular, what do we call those 2? X and Y. So when you're changing from polar to rectangular, the goal is to take an R and a theta and make them into an X and a Y. All right. So let's pretend that I give you a point in polar right there. If that's a point in polar, what are the 2 things you're going to know about it?
It's gonna have an angle.
You'll know the angle, yep, and you'll know the radius. So I'm going to draw the 2 things you know. You know that.
No triangle. There's hold on. No triangle.
No triangle?
We don't do that here.
All right, we won't call it a triangle.
All right.
You'll know the slope.
A 3-sided shape.
Now we need to draw a trigon.
Oh my
complete.
goodness.
We're going to draw a trigon. And we're going to make our trigon by drawing a vertical from that point straight down. What would the bottom side be called?
Adjacent.
That's not the position of it. I'm looking up for a name. from here to here, yeah, that's a horizontal distance, and usually we call that x. How about the vertical distance?
Is that one Y?
That's y. So our goal is to figure out a formula for x and y, and we already did this yesterday when we did parametric equations. It's going to be it's exactly the same thing. Yep.
So radius is technically like a slope.
Actually, see.
Well, the radius is, it has a slope. You're not going to need the slope for anything we're doing.
Okay.
That would involve tangent.
Because I'm thinking it has like an x and a y.
It has an x and a y, yep. But you won't actually need to know the slope of the radius for these two formulas.
Got you. Okay.
What trig function would involve this side, and that side?
Side angle side.
Well, that would be the way the information is laid
Oh
out,
my god.
side angle side. But we're looking for a trig function,
Oh.
like square root, cube root. It's not those. Yeah.
Is it like cosine
Yeah.
theta?
Let's start with that. Cosine, and now fill it in. You said theta,
Yeah, and then x over r.
adjacent over hypotenuse. And now we want to get x by itself, so we have a formula for x. How would you get x by itself?
Multiply
Multiply by
r.
r. That is the formula to convert an r and a theta into an x. You take r, you multiply by the cosine, and that will give you the x value. And you'll know the r, because I'm going to give that to you in the problem, and you'll know the theta. All right. Now, the other value you need, if you're trying to get something in rectangular, you also need to know the y. All right. So I'll do the same thing again. I need a trig function that involves the side that I don't know, the side that I do know, and the angle that I do know.
Would it be r sine theta?
Yeah, it's going to end up being r sine theta.
Is x always cosine and y always sine?
Cosine always has to do with the x, and sine always has to do with y. Yep.
I can remember.
Or tangent.
I did.
Yeah, we're not going to use tangent. Is going to be for the last thing.
Or tangent.
We don't need tangent for this. Okay, so those are the two formulas that you need to convert from polar to rectangular. R cosine theta, R sine theta. Okay, let's try an example. So convert to rectangular. 2 negative 200. Now, whenever this one, it's not going to happen. But whenever you deal with an angle that's a multiple of a 30 or a 45, we know those are on the unit circle. There's two special numbers that could come up. When we do our calculations, if you see the number 0.707 come up, 0.707 is a special number we've talked about. It's the square root of 2 divided by 2. Oh. Square root of 2 divided by 2. 0.707. That's a number from the unit circle. People remember root 2 over 2? Okay. So if we see this decimal, we need to use that number instead. There's only two special numbers. Anybody remember the other special fraction that came up on the unit circle? There was root 2 over 2 and, yep. Yep, it was root 3 over 2. This one comes up in the 45 triangle. This one comes up in the 30, 60, 90. Root 3 over 2 is 0.866. Those are the only two numbers that come up when we do these calculations that could be special. So do I do a special one? Yes, I do. I'll do a special one next. Now, 200. Is 200 a multiple of 30? No. Is it a multiple of 45?
Sure. I actually don't know.
Here, I'll just.
Like if you divide 200 by 45? No.
It's not.
So this particular problem, you're not going to see either of these two numbers, okay? Because this is not a multiple of 30 and it's not a multiple of 45. Okay. So let's find our values. What's the formula for x?
R cosine theta.
And now what if you fill in our numbers to what you just said?
2 cosine theta.
2 cosine
Why? Oh, wait, what?
negative
I mean,
200.
Because that's what they
And the formula for y? Yep.
This is going to be 2 sine negative 200 degrees.
So when you're converting from polar to rectangular, what you're really doing is you're finding the length of the bottom of a triangle and the height of a triangle. That's how you convert polar to rectangular. Find the base, find the height. Okay, now you just have to plug those in and see what they come out to. So 2 cosine negative 200. But what do I want to check on my calculator before I hit enter? Yeah, I'm in radians. This is in degrees. Okay, I'm not saying that you're going to have radians or you're going to have degrees all the time. You could have either or. Okay, so the x value is negative 1.88. And the y value is 2 sine negative 200, about 0.68. 2 decimal places is good. And now write your final answer. That's your x. That's your y. And that is your final answer. So this is the point in polar. This is the exact same point in rectangular. Any question on that? And I can show it's the same. I think I have a grid up here. Yeah. So this is the point 2, negative 200. I went 2 to the right, 2 units right, and then I rotated 200 degrees clockwise. Well, if I go halfway, how much is that? 180. Each line here is 15. So this brings me to 195. And then I just went a little bit past 195. Does anybody think that this point is in the wrong spot? 2, negative 200. So what I'm going to do now is I'm going to keep that point right where it is, but I'm going to change the grid behind it to be rectangular instead of polar. And let's see if it looks like it's at those coordinates. Let's do that. Okay. Does it look like the x value is about negative 1.9? Yep. And does it look like the y value is a little bit more than halfway up?
Yeah.
Yep. That's exactly where it should end up. Isn't that cool? I wait all year to do that.
That's pretty tight.
That is pretty neat. How did they know
So
that?
that's the point in polar, and that's the same point in rectangular, just changing the background behind it. The only reason that works is because the polar and the rectangular are the same size spacing. If you didn't use the same size spacing, it wouldn't work. Like if I use this really small grid, well, it's the wrong scale. It's not the right size graph paper. That's the right size graph paper that makes it work. Okay. Let's try this one. What's my formula for x on this one? Yep.
3 cosine 5 pi over 6.
6.
It's going to be easier to remember.
And my formula for sine? Yep.
3 sine 5 pi over 6.
My formula for y? 5 pi over 6. Now, 5 pi over 6. What's pi over 6? 30. So 30 times 5 is definitely a multiple of 30. So we are going to get these special numbers. Okay. Don't worry about the 3 yet. Just do the second part. If you do the 3, it's going to mess us up and we won't see these two numbers. We'll see these numbers tripled. That'll be confusing. So leave the 3 where it is. I'm just going to type cosine 5 pi over 6 and see what that is. And what do I have to do on my calculator?
Put
I have to switch over to radians. Switch to radians. Okay, I got negative 0.866. So what do I want to put inside the parentheses? This is a special one, so I don't want to put negative 0.866. I want to write down something that means the same thing, but it's exact. Yeah?
Square root of 3 over 2.
No, not the square root of 3 over 2. Square root of 3 over 2 is not negative 0.866. Yep.
Would be negative square root of 3 over 2?
Right, you have to put a negative with it. So negative square root of 3 over 2 is exactly that number. And that's the number you want to use. Okay, and now we'll do the bottom one. Sine 5 pi over 6. Well, if one of them comes out with that number, the other one will come out nice. Okay, that's 1/2. Okay, so our coordinate is going to be negative 3 root 3 over 2. That's what you get when you multiply your x, and your y, 3 over 2.
And that's the same universally even if you use radians or degrees?
No, I had to use radians because this problem was radians.
Yeah, but like you'll still get the same answer if you convert it to degrees.
If I change this number to 150, yes. Yep. I'd have to change that number to 150, and then I could do it in degrees. Yep. Okay, any question? So that's polar to rectangular. Last thing, changing the other way, rectangular to polar. So in rectangular, what do we call the two things that I give you? So in rectangular, what do you call the two things that I give you in a coordinate?
X and Y.
Yep.
The radius and the angle?
Not in rectangular.
Oh, x and y.
X and Y. So this is the same thing we just did right here, except it's the other way now. So rectangular, I give you the x and the y. And what's the goal in polar? You need to get the
Radius and the thing.
you need the radius and you need the theta. Okay, so we're going to draw a picture and see if we can figure out how to get the r and the theta. So here's actually I don't even need a circle yet. Here's a point, and that's in rectangular. So what's the two things you're going to know about it?
X and Y.
You're going to know the x and the y. So you're going to know how far over you have to go. And what are we going to call that?
X.
That's the x. And then you're also going to know how far up. What's that?
Y.
That's the y. And that was making 90. Okay. We need the r and we need the theta. Where's the r?
X and Y. It
Yeah.
makes a triangle.
It makes a triangle. That is your r, which is the hypotenuse of that triangle. If you're thinking, well, how is it an r? Because there's no circle. Well, you could put the circle in like that. Now it's the r. And if you knew the x and you knew the y, how would you find the r?
Pythagorean theorem.
So when you're finding r, one formula we'll need to use is Pythagorean theorem. Here's my angle. How would you find that angle if you knew this side and you knew that side? What trig function?
Tan.
Tangent. Yep. We're going to need tangent. What's the formula for tangent? It's
Opposite over hypotenuse.
no, that's sine.
Adjacent.
opposite over adjacent.
Oh, wait.
Opposite over adjacent. Now, that's not theta, that's tan theta. How do you get theta by itself in that equation?
No, wait, it's the negative one thing, the tan thing.
Yeah, because it's a function, we can't divide. Yep.
Take the inverse of tangent.
You have to take the inverse tangent on both sides. That is how you calculate your angle. So I'm going to write this nicely, but that's where the formula is going to come from. Inverse tangent will calculate the angle. Pythagorean theorem will calculate the r. All right. So let's write this nicely. So the first thing we want to do when we are changing to polar is you do want to know the quadrant. You might look at it and be like, well, I didn't really talk about the quadrant here, but you do want to know the quadrant. Which quadrant is that point in? Yeah, that one's in quadrant 1. And the reason you need to use the quadrant is because when you are in quadrants 1 and 4, the formula is exactly what we just wrote down up above. It's inverse tangent y over x. That's what we had right here. It's the inverse tangent of y over x. But the problem with inverse tangent is inverse tangent always gives you an answer here. What quadrants does that cover?
1 and 4.
It only covers 1 and 4. So if you want to get an answer over here, how far away is this other side? Like if you wanted to rotate and end up on the other side and go halfway around this circle, how much would you have to rotate to go halfway around? Yep.
180.
How much?
180.
180. So if you want an answer on the other side of the circle, you have to go like this. Okay, so if you want an answer in quadrants 2 or 3, it's almost the same formula, but you have to add pi. Why do you have to add pi? Because it puts you halfway around on the other side of the circle.
And it's only for theta, and the radius is the same.
Right, radius is the same. So, which I haven't written yet, but I will. So, inverse tangent y over x in quadrants 1 and 4, pi plus inverse tangent, or 180 if you're doing degrees. Now, where else could you have an angle besides quadrants 1, 2, 3, or 4? There's still somewhere else. Yep.
Yeah.
You could be right on the axis. Well, if you're on the axis, those angles are the easiest ones. You just have to memorize 0, 90, 180, 270. And how do you know if a coordinate is on an axis? Just looking at it.
It's on the line.
Well, it would be numbers.
It's built with 90. Like if part of it's 90.
So if I give you a coordinate, how do you know it's on an axis?
Sorry, I thought you meant angle.
Yep.
There's a 0.
There has to be a 0 in it somewhere. So if I give you a coordinate and it has a 0 in it, then you know you're on an axis. Depending on where the 0 is, it could be the x or it could be the y. Okay. So that covers how you find the angle. It's either inverse tangent y over x, 180 plus the inverse tangent, or the easiest case, you're just on an axis. And then what did we say for finding r? What do we use for that?
Pythagorean.
We just use Pythagorean theorem. Yep. R squared. I'm not calling it ABC because we're using r, x, and y, but it's just the Pythagorean theorem.
Would it be better to write it as r squared equals x squared plus y squared, or r equals the square root of x squared plus y squared?
You could write it either way. Yeah, if you wanted to write it this way, you could. Yep. Same thing. You're going to have to take the square root anyway when you go to solve it. So. All right. So let's try one converting from polar to rectangular. And I'll leave this up so you can look at it. Okay, 3, -5. First step, what quadrant is 3, -5? It's in quadrant 4, somewhere right around there. I'm not looking for an exact sketch, I just need to know the quadrant. Right 3, down 5. Okay. What's the formula to find your angle if you are in quadrant 4? Bert?
The theta equals the inverse tangent of y over x.
Yeah. So inverse tangent of y over x. What's y in this case?
-5.
Yep. And what's x?
3.
Okay, so we'll just see what that is. So inverse tangent of -5 over 3. Second inverse tangent. You could do it in radians or degrees. I'm going to do it in degrees. So that angle is -59.04. And that makes sense because it's rotating this way. -59 degrees. What if they didn't want the answer with a negative angle? What could you add to that to make it positive? You could plus 360 to it, and then it would bring you to the exact same point on the other, going the other way. They didn't say we couldn't use a negative, so I'm just going to use the negative angle. All right, and how do we find our radius? What's our theorem? Yep.
Pythagorean theorem.
Yep, we use Pythagorean theorem. Think of it like this. Find that segment in purple by making this triangle. That's a 3. That's a 5. Okay. What's going to be my formula to find the length of the purple segment? Yeah.
It'd be 3 squared plus -5 squared.
Yep. And then we're going to take the square root, and that'll cancel out that. 3 squared is how much? 9. And 5 squared? 25. And 9 plus 25? We'll just leave it like that. So to write this answer in polar, your radius, your r is square root 34. That's the purple distance from this origin to the point. And the amount of rotation is -59.04. So that's the reverse of what we just did in the last problem. Change it the other way. Any questions on? So we'll go over the homework on that tomorrow, and then our last section will be 10.1. Okay, so the homework, page 492, is 1 through 14.